Great. So I'll start today's talk by giving you a few examples of what I mean with having non-experts to train machine learning models and machine teaching. Of course, these videos are not the unique work in this domain, because there've been a lot of prior work starting 1983 at least. But these are more recent examples, and they have reached a broader audience. So here I'm going to play a video from Google, a system they call Teachable Machines. And the idea here is to make it easier for anyone to start exploring how machine learning works. The interface allows you to teach a simple computer vision model using your camera live in your browser without requiring from the end users to know any coding. So the interface looks kind of like this. You have the perspective of what your camera shows on the left. Then in the center is the 3 classes that you can train. You can see your training examples and how well they perform. And on the right, you have the mapping to each of these training examples of the classes. Once they recognize, what should they be triggering? Either it's an image or a sound or a speech, a dictated message, perhaps. So allow me to play this video, and John, please let me know if the rest, the audience cannot hear this. So this is simply an example of what one of the end users on the internet who found this interface decided to choose to do. In the first class, it trains one origami, the second, and the third, no origami at all, and is able to create this interactive, someone could call it art, through these interfaces. Now, moving things outside of a browser, Bjorn Carmen and others had a project in 2017 called Objectifier. And in this other video that I'm going to play now, you can see people teaching a camera embedded in this white device on the bottom right. And this device is connected to other home devices in the user's home and is able to recognize and respond to the user's actions that the user selected. So let's try to show you a few examples.
Okay.
This first case, the user was trying to train the lamp to open and close based on the book. Here the user is trying to train the record player to stop and start, and now we have another example with the electric kettle, on and off based on the mug. And my favorite one, this last one, where the end user is trying to train the bedroom lights to go on and off based on their movements with their device.
Actually works really good. I don't need to train it that much.
Great. So these are only a few examples within the larger machine teaching paradigms, but they're quite related to the work that I will be presenting today. So what's interesting about this example is that, as Bjorn Carmen puts it, they give an experience of training an artificial intelligence to people, to end users who have no expertise perhaps in machine learning. And this declares a shift from a passive consumer to an active, playful director of domestic technology. And I would argue that is beyond being playful and beyond domestic technology. By providing end users with an opportunity to directly manipulate what Amershi and others calls AI-infused systems that have features harnessing AI capabilities that are directly exposed to the end users. In this case, machine teaching can have broader implications for accessibility and inclusions, creativity, privacy, education, explainability by, once users have been exposed to machine learning models and some of the concepts of how they work, that changes also language perhaps that the model should explain their behavior. Provides users control and perhaps can have implication on trustworthiness of the systems as we expose non-experts to these black boxes. In my research group, we're mainly focusing on two of these aspects. One is creating innovative assistive technologies that can help people with disabilities and older adults to fine-tune the behavior of these systems to their own idiosyncratic characteristics and environments. One such example is enabling people with visual impairment or blind users to train fine-grained object recognizers about objects that occur in their environment, and as well as using participatory design methods to look at how children interact with such machine teaching applications and what are some of the concepts that they are able to uncover just by interacting with them without being explicitly taught. But I'm happy to discuss with you some of other efforts related to other aspects. And I think explainability and machine teaching really relates to what Gary talked in the first session about self-explainability, and specifically one of the points in his scorecard related to diagnosis of failures, where we allow the user to manipulate AI and infer the diagnosis. Today, I will narrow down some of the work we're doing to one of our most recent publication at CHI 2020. This is one of the main venues for publishing human-computer interaction research. And here what we do is that we examine how people conceptualize, experience, and reflect on their engagement with machine teaching. To better contextualize our observation, we really focus on a fine-grained object recognition supervised image classification task. More specifically, what we do, we ask 100 participants. These are recruited through Amazon Mechanical Turk. And we ask them to take photos of everyday products such as soda cans, cereal boxes, and spices to teach their phone to automatically recognize them. They could choose up to 3 objects, and all these objects have to be in the same category. So really care here about fine-grained recognition. For example, 3 different soda cans. And we employ here a performance-based payment scheme. Participants are called to iterate and reflect. So we do get qualitative feedback also from the participants. And they have to reflect over the efforts with the goal of making their recognition models more robust. Amazon Mechanical Turk here, it's not that only allows us to recruit quickly a large group of participants, but more importantly, this test bed is deployed on the mobile phone of the users. So we really wanted to collect data that are beyond a lab in people's homes with different real world environments, illuminations, and other characteristics. So at this point, I'd like to point out that while this might seem a naive application, having people train a simple app to recognize 3 soda cans, we opted for this task that in a sense that is accessible. People can choose anything that is in their environment, right? And is limited in time. You only have 3 classes to train. But most important is a task where humans are extremely good compared to machines. Since they possess prior knowledge of the image classes, they can recognize this object anywhere, anytime. In this way, they can serve as the oracle. So Zhu and others back in 2018 provide us with a better vocabulary for positioning this task, as well as some of the previous examples that I showed you in the videos, in a broader machine teaching paradigms where they look at who is the teacher and who is the student, and what are the teaching strategies and perhaps assumptions during this process. So using this framework as a design space, we can describe our problem as a machine teaching task where human is the teacher and the object recognition model is the student. And in this case, we have only 1 student. So each participant has to train 1 unique model, their own personal model. The teacher provides in batch mode a pool of examples, which is finite. Here, the teaching signals basically is just a bunch of labeled photos of objects, specifically 30 photos for each object. And here, the teacher takes a model-free approach. What that means is that it's treating the student as a black box, having no knowledge on how it works. And indeed, we recruit participants from Amazon Mechanical Turk that are not expert in machine learning. More so, the student in this case, it's the convolutional neural network, does not anticipate teaching. And what I mean by that is that assumes training examples are independent and identically distributed, and that there are no errors. The teacher here is considered a friend, which means that no adversarial teaching. And last, our participants use heuristic teaching methods to improve the performance of the models. And the goal of our study was to better understand these heuristic methods, the factors they may relate to, as well as assumptions that non-experts might have when teaching machines. I invite you all to read our paper for more details and pointing limitations, the design of the study. I'll try to share with you our observation in a nutshell. So when looking at participants' teaching strategies, we observe that mainly tend to teach with clear representative examples. So what it means in this task is that they tend to include in the majority of their examples the logo or whatever viewpoint of the object has more discriminative features for the model to learn. This is promising. Sometimes participants incorporate examples that are closer to the decision boundaries, so a little bit more confusing examples, and they do so by employing variation. And we've observed here that 77 out of 100 participants diversified their training examples. And more than half of them mentioned diversity as being important. This is promising because we know in machine learning, if you have larger diversity in your training examples, your model will generalize better. Now, when we look at how humans would perform a similar task, right, object recognition, we look at the work from Thomas Palmieri and Isabelle Gauthier, and they write for humans that object recognition involves generalization across size, location, viewpoint, and illumination. What's interesting is that we find the participants try to make their models also generalize across these four dimensions by having 65 of our participants incorporating variation in object size, 39 of them in object location by placing the object against different backgrounds, as you can see here. 63 included different viewpoints, perhaps by rotating the object, and 19 changed the illumination of their training examples. So really it was very few, 11 participants that varied all four of these dimensions. It was interesting to see that participants, without being primed, when they were asked to describe their strategies, a lot of them mentioned words that there's a need for diversity with terms like different, various, all, multiple, every, variety, different, combined with words like angle, views, side, facets, background, lighting, distance, and positioning. So they are using similar terms by drawing parallels to how humans perhaps perform object recognition when they were trying to train the machines to do the same. Now, one of the limitations pointed from prior work when non-experts train machine learning algorithms is class imbalance. That means that they would use different number of examples across the classes that they have to train on. In this case, the number of training examples was fixed at 30 examples, but we do observe that non-experts can have disparate treatments across their classes in a different way. And we observe here that way is by having inconsistency in variation. So for example, for one of the objects, they may vary the size, the viewpoint, and the illumination, and for the others, none of those, or a different one. So this is something to anticipate when designing such interfaces. Now, when looking at how participants test their models to see if they are robust, we observe that very few diversify their testing examples, with model breaking examples being almost close to none. So this is problematic, and it was perhaps not a big surprise to see that many participants wanting to change nothing or being satisfied with the performance of their model or not knowing what to do next when we ask them, what would you do if you have a chance to train the model a second time to improve it? Because they chose, typically for testing their models, very representative examples, as you can see here in the examples. And so the model were always performing well. And so they're like, yeah, it works perfect. So I don't need to do anything else to make it work better. Now, looking at other misconceptions, we find that this concept of consistency is a prevalent one. While it's true that consistency between training and testing data will result in better performance, assuming they both represent real-life examples, some of our participants thought that being consistent entails teaching with multiple identical examples, so including no variation whatsoever. So here I have a quote from our participant 6. This participant provided identical examples throughout the training, so 30 identical examples for one object, 30 for the second, and 30 for the third object. A participant says, I figure I need to be consistent when I took the picture, so they look similar. So they basically showed as an exactly the same example 30 times to the model to learn. Other misconceptions relate to machines' capability for reasoning. For example, we noticed that few participants would try to provide, after changing the orientation and the size, they would try to provide examples from the contents of the objects inside, which have visual characteristics totally different from the objects and how they were trained on the model. And so this could add confusion to the model. Others would assume that the model was able to infer the text on the objects, and then that's what the information that it stored for recognizing them. Now, to wrap up, I believe that machine teaching has broader implications for innovation and AI literacy. And we see how our results, some being new insights, others strengthening prior empirical and anecdotal evidence, can help better understanding non-experts' interaction with machine teaching. Some of our recommendations for the design of future teachable interfaces highlight the need for accounting for non-experts' teaching strategies, helping people to better craft their evaluation example, specifically those examples that can break models to understand the limitations of their models, as well as anticipating common misconceptions. With this opportunity, I'd like to thank my students, as well as NSF and Meidler for this funding support, and thank you all for listening. I'd be happy to take any questions or comments.